The 4 basic mathematics problems that seem simple but no one can solve. We all deal with mathematical problems on a regular basis. Some math problems are simple and not difficult to solve, and some are complex and difficult to solve. However, there are still some mathematical problems, which seem surprisingly simple, but it turns out that no one has been able to solve them so far. Here are 4 basic math problems that look simple but are actually complex and difficult to solve. They have always been difficult problems in mathematics and computer science, and many mathematicians and computer scientists have been trying to solve them. The first one, Collatz Conjecture. The Collatz Conjecture, also known as the 3n+1 conjecture or the Ulam conjecture, is one of the most famous unsolved mathematical problems. It is so simple that it can be simply explained to an elementary school student. The problem goes like this: if you start with any positive integer x, and if x is even, divide it by 2, and if x is odd, multiply it by 3 and add 1, and repeat this process with the resulting number, you will eventually reach the number 1. This looks very simple, right? But it is a deep and mysterious mathematical problem. Despite numerous attempts, mathematicians have not been able to prove the Collatz conjecture. While it has been verified for all numbers up to 2 to the power of 68, there is no proof that the sequence will always terminate for all numbers. The conjecture is widely regarded as one of the most difficult and intriguing open problems in mathematics, and it has implications for many areas of number theory and computer science. Paul Erdos, one of the most prolific mathematicians and producers of mathematical conjectures, said about the Collatz conjecture, "Mathematics may not be ready for such problems." He also offered a prize for its solution. Jeffrey Lagarius, who has written several highly cited papers on Collatz conjecture, stated in 2010 that the Collatz conjecture is an extraordinarily difficult problem, completely out of reach of present-day mathematics. The second one is the Jacobi Conjecture. The Jacobi Conjecture is a difficult problem in mathematics. It asks whether every polynomial mapping from n variables to n variables that is invertible can be expressed as a composition of a linear transformation and a polynomial mapping with constant Jacobian determinant. In other words, the conjecture asks whether every polynomial function that is invertible and does not distort volume can be written as a combination of linear transformations and polynomial functions with constant determinant of the Jacobian matrix. The Jacobian matrix is a matrix of partial derivatives that encodes information about how a function changes near a point. Mathematicians have been working on this problem for decades, but have yet to find a full generality proof or counterexample, and it continues to be an active area of research in algebraic geometry and related fields. The Jacobi conjecture is of great significance to the fields of algebraic geometry and topology. If it holds, it will provide us with a deeper understanding of polynomial maps and their properties, and if it does not hold, it will challenge some basic assumptions in algebraic geometry, and suggest that there are some more complex polynomial maps that cannot be used in the Jacobi conjecture. The third one is the traveling salesman problem. The traveling salesman problem, TSP, is a classic problem in computer science and optimization that asks for the shortest possible route that a salesman can take to visit a set of cities and return to his starting point, while visiting each city exactly once. The traveling salesman problem has a wide range of applications in real life, such as route planning, circuit wiring, genome sequencing, data compression and other fields. The various heuristic and approximation algorithms have been developed to find approximate solutions to the problem, including the nearest neighbor algorithm, the 2-opt algorithm, and the Lin-Kernighan heuristic. The traveling salesman problem looks simple, but when the number of cities increases, the computational complexity of finding the optimal solution increases exponentially, making it very difficult to solve the problem. In fact, this problem has been shown to be an NP-hard problem, that is, it is impossible to find the optimal solution for large instances of the problem in a reasonable amount of time. The fourth one is P equals NP problem. The P equals NP problem is an important and fundamental question in computer science and mathematics, which asks whether the set of problems that can be solved efficiently in polynomial time, is equal to the set of problems that can be verified efficiently. The P refers to the class of problems that can be solved efficiently, while the NP refers to the class of problems that can be verified efficiently. If P equals NP, then every problem whose solution can be verified in polynomial time can also be solved in polynomial time by a nondeterministic Turing machine. This would have far-reaching implications in computer science, including the ability to efficiently solve many difficult problems such as factoring large numbers and optimizing complex systems. However, despite decades of research and numerous attempts, no one has been able to prove whether P equals NP or not. The problem is widely believed to be extremely difficult, and most experts believe that it is unlikely that a proof will be found in the near future. Nevertheless, the problem remains one of the most important and unsolved problems in computer science and mathematics.